Nullstellensatz. That's a cool theorem that people don't know about. So I will tell you about the real outside constants. I will tell you about the real Nullstellensatz. Okay. Now, of course, everybody knows about the classical Nullstellensatz. If you take a commutative algebra class or introduction to algebraic geometry, you learn about the classical Nullstellensatz. So let me state the classical Nullstellensatz, and there are many, many versions. You know, discrete math, people talk about combinatorial Nullstellensätze. So let me give you one way of stating the classical Nullstellensatz over C. So polynomial system. Of equations. f1 of x equals 0, blah, blah, up to fr of x. So x is a vector of unknowns. It either has a solution say in n variables, or so either the system has a solution or there exists a witness. There exists a witness that proves to you that there's no solution. Okay? So the witness in this case can be phrased as follows. There exist polynomials P1 up to PR, multiplier polynomials P1 up to PR, such that P1 F1 plus P2 F2 blah blah up to PR FR is identically 1. It's the one polynomial. Okay? Partition of unity. Right? So either you have a system of polynomial equations, either there's a solution, or there is, you know, quote unquote, a dual solution in this sense. Right? So a dual solution is a linear combination of the given equation. That's 1. Okay, that's the Nullstellensatz. So that's a very nice theorem, right? So you can think about it as, you know, suppose you actually want to solve the system, right? So, well, that translates this into a linear algebra question. Rather than asking, does there exist at x, you can ask, do they exist P1 up to PR? Right? That's a linear algebra problem. And, you know, this is not so difficult to do, right? So how do you find this? Right? So, well, no, how to do this? You do this with the extended Buchberger algorithm. Okay. Just like in freshman discrete math, right? We teach the Euclidean algorithm, and then one, you know, your bunch of integers, and then, you know, the GCD can be written as a linear combination. If the GCD is 1, right, then you can write 1 as an integer linear combination of the given numbers, and you do that with the extended Euclidean algorithm. For polynomial, you use the extended Buchberger algorithm. So to get this, you just run the Grobner basis, you keep track of what you're doing, right? The Grobner basis, the reduced Grobner basis is 1, and then you pick up the multipliers P1 up to PR. Okay, that's the classical Nullstellensatz. Easy. Okay. Let's talk about linear programming duality for a moment. So I stated linear programming duality today. Again, there are many other ways of stating linear programming duality, but let me state it this way. Okay. So a system of strict, I'm going to phrase it for strict, but there's many other ways. Strict linear inequalities, we call them H1 of x greater equals 0, greater 0, blah, 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 HT of x strictly greater 0. So you have a linear system that says a bunch of linear functions with the constant allowed. Now, H1 is strictly greater 0, H2 is strictly greater 0, and so on. Either has a solution, in R to the n. Now we need an ordered field. In fact, we need a real closed, well, here we just need an ordered field. So we need an ordered field, so either it has a solution or there exists a witness. And the witness here again is a bunch of multipliers, a1 up to a2, and these are non-negative real numbers, but not all 0. Okay? So it's a real vector of length t, non-negative, but not all 0. Right? So it exists a non-trivial, non-negative multiplier vector such that the linear combination is 0. a1 times h1, a2, h2, blah, 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 ht equals 0. Okay, let's think about this, right? So if I can find those multipliers, a1 up to at, then you're convinced that there's no solution, right? Because suppose there were an x, right? Well, then all of these, are strictly positive. The a's are non-negative, and at least one a is positive, right? So these are a bunch of non-negative products, at least one of which is strictly positive. But if you add up a bunch of non-negative numbers, at least one of which is strictly positive, you can't get 0. Okay, so but the meat is the converse, right? The hard part is that that's an if and only if, right? So whenever Abraham gives me an infeasible system, then there will be some multipliers a1 up to a, and you find that again it's easy, right? So how do we solve linear programs? Right? By either the simplex method or interior point methods, and both of these will supply, if asked, the dual solution. So these are two easy theorems. The classical Nullstellensatz over an algebraically closed field for equations, and linear programming duality for linear inequalities. Wouldn't it be nice if there were a common generalization? Wouldn't it be nice if there were a theorem like that works over the real numbers, but not just with linear inequalities and linear equations, but also with non-linear equations and non-linear inequalities? Maybe in a course on non-linear algebra one might hear about such a theorem, right? Because now we're dealing with non-linear things. So let's state the theorem. So now we're going to look at a general system of arbitrary polynomial equations and inequalities. Normal equations and inequalities. And I'm going to call my system star. So first of all there's equations f1 of x blah blah, f1 f of r x equals 0 and n variables. Then we have some weak inequalities, g1 of x greater equals 0, blah, 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 up to gs of x greater equals 0. And maybe we'll also allow, h1 of x strictly greater than 0 up to ht of x. Okay, and we take the conjunction of all of these. Okay, so that's a typical system. So that's a system that describes a basic semi-algebraic set. Not closed necessarily, maybe open, maybe closed, maybe neither. Okay? So we want to know, does there exist an X? So here's the real Nullstellensatz. So either our system star has a solution, in R to the n, or there exists an identity, or there exists a witness, or there exists a polynomial identity. or there exists a polynomial identity that convinces you beyond any reasonable doubt, as they say in the TV drama. Okay, beyond any reasonable doubt that there is no solution. Okay, and it goes like this. The identity has this form. So first of all, there's a linear combination of the given equations, AI, Fi. So this is the ideal part. Right? So these are polynomials. So everything now is polynomial. So given polynomials f and g and h, we're going to find some other polynomials, a, b, c, d. I'm going to fill the blackboard now. This is a longish condition. Right? So there exist some other polynomials, a1 up to ar. Okay, buckle your seatbelt. I'm going to fill this now. Okay, so, and here we have a sum over all nu in 0, 1 to the s. Okay, so binary vectors of length s. That takes care of the weak inequalities here. And then the multipliers are sums of squares. So sum j b j nu squared times g1 to the nu 1 times g2 to the nu 2 up to gs to the nu s. Okay? And this is a finite sum. Okay? So there exist finitely many polynomials, you know, b something something, b11, b12 up to b711. Okay? And then I take square-free products of the g's. So I'm allowing to multiply g's, but only square-free products. Okay, goes on. So then I allow the same thing for the h's. So a sum nu in 0, 1 to the t, sum over all j, c j nu squared, h1 nu 1 up to ht nu t. Same thing. There exists, you know, polynomial c and more. You know, then there is a single sum of squares. We're allowing a dk squared, and then finally we're allowing a product. So right now we have a symmetry in g and h. Right. So right now they're created equal, but in the system they're a little bit different. So I have to break the symmetry between the weak and the strict inequalities, and that's the last term. L1 up to t, ht, and ut now that these are, sorry, ul I guess, I'm sorry, ul, and these are non-negative integers. So this is all 0. Okay. Okay, so let's take a moment to let this sink in. Okay, so suppose I have my polynomial system, and then, you know, I want to convince you that there's no solution. I give you an identity like this. Okay? Well, why are you convinced? Well, let's think about it. Suppose there were a solution x, and we plug in, right? Well, then this evaluates to 0, right? Because the f's vanish. So this is 0. This, whatever it is non-negative, right? Because the g's are non-negative at my point. They multiply them, they're non-negative. The multipliers are sums of squares, they're non-negative, so this is non-negative. Okay, so we have 0 plus something non-negative, plus something else that's non-negative, plus something else that's non-negative, plus something that's positive. Okay, so I allow t to be, so the empty product is 1. Okay, so if there are no h's, so if t is 0, then this is 1. But whatever this product is, it's a product of h's. It's a product, possibly empty, of things that are strictly positive, and that's a positive number. So we have a bunch of non-negative things plus something positive is 0, and that's a contradiction. Okay.
Just a quick question.
Yes.
We are in our sum. We are taking the nu to be one of the possibilities to be all 0. So we have.
That is correct. Okay. And then yeah, that would, I guess. Maybe that would subsume. Why am I having this? Maybe I don't need this. No, okay, that's okay. Good. If nu is all 0, then that covers that case. Good. Well, and there are other. I mean, there are different ways of writing this, but this I think is the correct statement. Okay. So the punchline is that that's an STP. Let me write this in yellow. Punchline. Finding such a witness, such a Nullstellensatz certificate, real Nullstellensatz certificate, in bounded degree that's important, in bounded degree is an STP. So in bounded degree says, well, my given polynomials, the f's, the g's, and the h's, they have some degree, at most 7. Okay? And now I want to, find these multipliers, but of course, a priori, this theorem doesn't tell me in which degree to look. Right? So I might have to have very high degree, but let's say I'm only interested in a certificate of degree at most 100. Okay? So that says if these f's, have degrees, up to degree at most, so then these multipliers at most degree 93, right? So whatever makes the individual expressions at most 100, right? So then all polynomials in sight, I can have unknown polynomials. What about these sums of squares? Well, you know now how to do this, right? This is linear because that's x transpose ax. So the sum of squareness, being a sum of squares, we sort of Koleski our way into phrasing this as an STP in degree. So we do exactly what we did all day. Right? We're phrasing this as an STP condition. We block them, block, 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 block. We have linear constraints. This is an STP. Okay? So that's good. So that's the real Nullstellensatz. The real Nullstellensatz says a system of polynomial equations and inequalities over the real numbers or any other real closed field, possibly with evaluation, has a certificate, either has a solution or it has an STP certificate in some degree. Okay. Let's see some examples.
But if STP cannot find such a thing of bounded degree, you cannot say for sure whether.
Okay, that's okay. Yeah. So, what about this bounded degree? Right. So that's a good question. So, so now we say I'm looking for a certificate of degree at most 100. If I find one, then I know there's no solution. Suppose I don't find a certificate. Well, maybe I should try 101, or 200. Or 359, right? So I'm taking your question as saying, is there a degree bound, right? So in the other case, in the Nullstellensatz, there's a degree bound, right? There's a literature, it's easy, so the linear algebra, right? So there's an easy degree bound. So does there exist a degree bound? Let me answer this as follows. What else should we do between the two workshops? Next week we have a workshop on optimization, then there's 3 weeks no workshop, then there's algebraic statistics. Huh? So we'll have more lectures at NIMS to which everybody is invited, and we can have lectures on stuff that we can learn. Or we can have new research. So we can stuff that already some of us know. So for example, we might ask Spencer to give a lecture on chip firing. Right? Chip firing is related to lots of things, probability, algebraic geometry, blah, blah. So you always wanted to know about chip firing and graphs, so maybe you want to know about chip, so we can have Spencer give an introductory lecture on the mathematics of chip firing. Right? Or we could all learn something we don't yet know. For example, the amazing new paper by Kostrua and her co-authors, I think Lombardi, Kostrua, Lombardi, I forgot the third guy. Okay. So there were known bounds. So the logicians have worked on that. So there's a tower of exponentials, right? So there's a 2 to the 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 2, whatever. Some crazy, it's not quite Ackermann, but sort of pretty bad, So there exists a bound. So the logicians have a theorem that say there exists a bound, okay? But they actually gave a bound. And I forgot, it was like triply exponential. So it's still crazy, but pretty good. Okay, so it's a long paper, 60 pages, that appeared on the archive a month ago, 2 months ago. Constance people have read this in the meantime. This was long in the making. So this paper took 25 years to write, and now it's on the archive. So we could, for example, one of us could present this paper. Right? So that's the answer. Right? So yes, there's a degree bound, and I would love to read it with one of you or two of you. Okay. Anyway, let's do some examples. Special cases. Special cases. So for example, if R is 0 and S is 0 and T is 1. Okay. So let's look at that case. So in that case, there's a single inequality. Well, then our system looks like this. So given a polynomial, is this system feasible? A single polynomial, can it be positive? Right? So, okay, so star is infeasible. So when is this infeasible? Well, that of course means that minus h is non-negative on Rn. Right? This has no solution if minus h is a non-negative polynomial. So now, that happens if and only if there's an identity like this, where R is 0, S is 0, and T is 1. Okay, so the identity looks like this. Sum J Cj squared H plus another sum of squares D, let me write like this, plus H to the U is the 0 polynomial, and here we can assume that the exponent U is either 0 or 1. Okay, so I claim, because this goes away, here T is 1, right? So there's only the square free product is either H or 1. And then, but here we have this term, right? And this one is either some power of H, but if it's if it's H to the 7th, we can pull out the H to the 6th and put it over here, because H to the 6th is the sum of squares. It's the square of H cubed. Right? So we can here either have an H, and that says, so you unravel this, minus H is a ratio of sums of squares. So this gives us Artin's theorem. Okay. So one of the Hilbert problems, 900 problems, was whether every non-negative polynomial can be written as a sum of square of rational functions. That was proved by Artin, I think in 1923, Emil Artin, and that's this special case. Right? So you take this identity. So there are two cases, right? So either, okay, so let's say U is 0, right? Then you take minus H, you bring this on the other side, right? Minus H over there, you divide by this, and then, minus H is a ratio of sums of squares. And the ratio of sums of squares is a sum of squares of rational functions. Okay, that's elementary. Okay? And then the other case, if H is to the 1, then you also do something similar. Okay? So this gives Artin's theorem. Okay? So Artin's theorem, stated one more time. So Artin's theorem, that's 7-6 in the notes. Every polynomial that's non-negative on R to the n is a sum of squares of rational functions. Okay, let's do one other special case. Let's do the special case where we have only equations. Let's do that special case. Okay, so just equations. again in that case. So S equals T equals 0, just equations. So when does a system of equations have no solution over the real numbers? So there's no solution if and only if there exists a certificate of the form sum I from 1 up to R AI Fi. So we have this part. Now I see. Let me put this back in, okay? Just to not outdo myself, let me put this back in. So if S and T are 0, then, I still want a sum of squares term. Okay, let's leave it. Okay, doesn't harm. Okay, so now we have this plus sum of squares over some k dk squared plus 1 is identically 0, right? So because now this product is 1. Okay, so there's no solution. Well, then minus 1 is still a sum of squares. Okay, so corollary. It's exactly the same theorem we had earlier. So if I be any ideal in the polynomial ring in n variables, now it's any ideal whatsoever whose real variety is empty, then minus 1 is a sum of squares mod I. Okay. Right, so we bring 1 on the other side, right? Then minus 1 is a sum of squares mod the ideal generated by the f's. Okay, so that's a special case. If S and T are 0, and the only problem is the degree bounds, right? So now, if the variety of I, a complex variety, is not finite, then the set B of standard monomials is not finite. So therefore, as we look for these representations, we have to work our way up, up in degree inside the infinite set B. And that's an active area of research, how to make good choices and so on and so on. Yes?
So let's go back to the Artin's theorem. So there H is a ratio of sum of squares. It doesn't say sum of ratio of squares.
Okay. That's an extremely good question. I feared that you would say that, so let's try that. Okay, so let's try. Okay, let's try a squared plus b squared over c squared plus d squared. I want to write this, so help me out, Rainer. So I want to write this as a sum of squares of rational functions. So how about okay, let me start. Okay. Well, it's not good enough quite yet. I think there was a trick that I now forget. There's a trick that lets us write this as a sum of squares of rational functions. And I just don't remember the trick right now.
Is there some geometric series trick?
No. It's just some identity. So a c squared. You want to take c squared plus d squared and replace it. How about okay, I don't remember. So it can be done, and maybe before 3 o'clock somebody will figure it out. It has to do with C. Okay, I just don't remember. There's a way to do it. Okay. let's end on an example. So in this afternoon, I want you to do one example. So let me show you one example, and just kind of to end on this. So here is a problem, x minus y squared plus 3 is greater or equal 0, and g is y plus x squared plus 2 equals 0. Okay, so here's a high school problem. We have the plane, we have the x, y plane, and we have this equation, that's a g. So the equation says that y should be negative x squared minus 2. So that's a parabola like this. Okay, that's this parabola. And then f greater or equal 0, that says we are in another parabola, something like that. Okay, so we want to show that the intersection of these two yellow sets is empty. Okay, that's a typical thing we want to do. So we want, for example, S1 plus S2F plus 1 plus S2 S3G, that should be identically 0, where the s's are sums of squares, where S1 and S2. Okay, right, because this S3 doesn't have to be this. S3 can be anything, so that's in the ideal generated by G, and then we have S1 plus S2 times F is equal to minus 1. That's what the real Nullstellensatz says. Okay? So the real Nullstellensatz guarantees in this picture, if we leave the picture, they don't meet, there will be multipliers S1, S2, S3, and whenever you or your kids or your nephew or whoever solves this kind of problem from now on, I want you to tell them that semi-definite programming comes to the rescue, right? So we type this into some semi-definite programming solver, and this one you can do by hand. So here's one solution. So for example, S1 you can take a third plus 2 times y plus 3 halves squared plus 6x minus 1 over 6 squared. And the other two are super easy, S2 is equal to 2, and S3 is just minus 6. Okay, so that's a certificate in degree 2. Right? So F and G are of degree 2, so I'm allowing S2 and S3 to be constants, and S1 I allow to be quadratic. Right? So I'm giving degree bound 2, write down the STP, and I get the certificate. So this proves now that the yellow parabola, the two parabolas don't meet. Okay, time is up. So problem sheets are over there somewhere. And so, yeah, right over there. So grab a sheet, discuss. I'll be around. And then at 3 o'clock we reconvene to talk about some solutions. And if you're interested in joining me for a hamburger, well, please do.